Thank you. Thank you for that introduction, Michael. I may ask you to talk to my wife later about the good listening part, because that would be a first, at least in my house. Good evening, everybody, and thanks for being here. I do realize that I'm the last thing between a long day, exciting one hopefully, and festivities for the evening, so I will try to be appropriately informative, to deal with, to be in sync with the part of the day that you left behind, and I will try to be maybe inadvertently funny, or give you the entertainment part of the evening that's coming up. So speaking about entertainment, if you look at the title of this foil, I've never had so many comments about the title of a foil as I've had on this one, including very well-meaning comments like, "You've got a massive set of typographical errors, please correct them." Even Microsoft got blamed as part of this title, saying, it couldn't understand a few of the fonts, and I'm sure you didn't mean double ampersands or double bars, right? Well, it turns out I did. And for those that go back to the good old days of programming in C, you will very clearly know what I mean by either the or at the end. I do apologize to my Fortran brethren, because I did get requests to turn this into .ands and .ors, but I decided to stay with the language I learned to code in. So what I want to spend time today is a topic, whether you're a technologist, whether you're a technocrat, whether you're an end user or you're simply interested in this debate, it will be valuable to you, hopefully. Because the issue that faces us is an issue across all of these domains. It's rooted in technology, it's rooted in end usage, but it has ramifications all the way up to how national governments decide to invest in these areas, in places converging investment and in places diverging investment. So we'll talk about whether the world has to be big data or HPC, a set of choices at the level of technology, set of choices at the level of investments, frankly, a set of choices at the level of how we look at the industry, or it can be a more converged and leveraged future. That debate is not new. I heard Michael say we've been discussing this in forums and other meetings, and I certainly have been part of this for a while now. As you will see on this foil, there are various places where not only is the debate happening, but there are points of view being put forward as to what the answer should be. It's really not the HPC and big data are related, but how are they related? I think the recognition that they are related at the level of technology that enables both is quite well understood. I mean, I rarely see people challenging that as vociferously as the political ramifications of keeping these two either separate or converged in terms of new programs to fund, new programs to enable. I know in the United States, for instance, I see Jamang sitting here. I think you will identify with this. There was a debate that was very much an HPC or big data when it came to what was exascale computing to be used for. And when people asked me, is it big data or HPC, I would simply answer yes, which that didn't make me a good listener, Michael, but apparently. Because the answer really is both, right? And it's a political and a funding question as to how you want to spin or position a fairly common set of investments. So today, I'm going to talk a little bit about the how from an Intel perspective, but perhaps more so from an ecosystem perspective as we look at the inevitability of data-intensive computing being kind of the expansion of our next frontier, and the inevitability of high performance or performance-sensitive infrastructure being part of enabling the full promise of the use of that data-intensive computing. Today, and a lot of the debate is rooted in this initial epoch state is they're different systems. They're different systems not only at the technical level, but they're different ecosystems as well. If you look on the foil, for instance, the HPC starts with how you view high-performance computing as an application developer or an user. And it starts with the programming model, which is fairly well understood. We do bulk synchronous. In the last talk, we heard about OpenMP, MPI, very well-established standards for doing that. Whereas big data, having grown up, or data analytics, having grown up in a different part of the kind of industrial landscape, has a very different population of developers that actually then drives to a different set of tools that's being used to develop those applications. And so that's more around Java and other interpretive high-level languages, with the focus being on simplicity of use, so that you can actually get the problem domains solved without a deep knowledge of high-performance computing. And then that difference of choices of things that go into the infrastructure and the resource manager and how we deal with data, the file system, down to the hardware, are actually fairly distinct, right? The question isn't whether they're distinct or not. The question really is, do they need to be distinct as we go forward? And if we do that, let's ask the question of what are the workloads and workflows going to do in the future? Because at the end of the day, that is the king, right? When I look at the world, a rather little simplistic view, there's really three axes. One is kind of the data axis, how much data there is, how complex is the data, how fast is it coming in. The other then is the compute. Depending on what you're trying to do, how much compute do you need? What's the scale of computation you may need, of aggregation, of system parameters being stressed? And then the third one is the solution urgency, which is, in simplistic terms, you'd say, is it real-time, near real-time, or offline? Because that then introduces a various set of choices on what you do with the infrastructure that you use to solve the problem. If you accept the proposition that in many cases, this is a cliche, time is money, that the economic benefit of going further out on the solution urgency axis is actually tremendously relevant economically, then it says there's a new class of what I would call fast data, which is a combination of a lot of data and the need to get a quick answer, whether you're in the predictive world or in the decision-making world, and the value of that time to answer increases as that time shortens. You get really to the point of fast data. It's not about how much data there is. It's not about how much compute there you could potentially use. It's about how fast you need to use the data that you need to use to make the decision you need to make, right? And while we've talked a lot about this notion of big data, and we've talked a lot about high performance, what we really ought to be thinking about is this notion of bringing the two together to add this notion of solution urgency, using the compute or the right level of compute with the right amount of data to get the solution, most importantly, in the right amount of time. So if we change this discussion a little bit from big data to fast data, this convergence place where we are going to have to be very sensitive to performance while we deal with vast amounts of data. Not just amounts, but complexities, modalities, as well, and representations. Then you have to ask the following question. The question is, from where we are today, which is essentially a distinct, perhaps with overlap, but a distinct set of design choices and ingredients at various levels of the infrastructure, to, as it's on the right-hand side of the foil, a single system architecture, but with enough configurability in it that you can actually serve different design points between compute intensive and data intensive. Why is this question even relevant? It isn't just an intellectual pursuit to say, can we do something like this? It is an economic imperative to do so. And depending on which side of the world you sit on, I don't mean geographically, of this debate, it is important to you in a different way. If you sit on the big data analytics side, and you look at a world which is more like the world today from here, right? You are increasingly challenged by inefficiency and ineffectiveness of having to recreate and reinvent a lot of things that have been done for the last 50 years in HPC. Right? Maybe big data is big enough, there's enough economic incentive to actually go there, but it is a damned inefficient process. If you're sitting on the HPC side of the world, you are essentially, if you don't look at the future of the single converged infrastructure and the ability for HPC learnings and infrastructure to affect this new surface of high performance compute, you're headed to being a dinosaur, right? Maybe the meteors won't hit, but over time you will not play in portions of the market. And that, at the end of the day, is the economic reality that will constrain the future use of HPC. So then the question is, what's the challenge? Okay, so we've got an economic incentive. Money usually, time is money, and money is the biggest motivator in business. So what's the problem? We recognize this. I saw a lot of heads nodding. The problem is, really, what it comes down to is the fact that when you build systems, you rarely have the luxury of building it for a single purpose. And the world of workloads is diverse enough, and the performance sensitivity is high enough that you can't have a globally optimal, locally highly suboptimal solution to all of these. It also breaks your economic model. If you're a supercomputing center that's trying to go out and win customers, and that is the basis of your growth, then you have to be serving their needs, even if they're very different needs. If you look at this chart here, this is the NERSC Hopper system. There are over 600 applications that run on that machine, right? And, yes, they're not all equal, but that's the point. Who decides who's more equal and who's less, right? If you look at the implications of that, and you look at all of these, whether you go from a code like LAMPS, or you go to a code like CSM, there was one more that was actually interesting. Oh, NWChem, for instance. They all have different levels of what we would call processor, memory, interconnect, and storage sensitivities. It is not a surprise, by the way, that the typical big data workloads, like a traffic monitoring system, is pretty heavy on storage, right? Personal digital health, that is a mass of data. On the other hand, if you've been working in oil and gas, for instance, in the upstream exploration part, for the last 10 years, not enough memory bandwidth. Right? What the right-hand side says is if your world's going to look like a lot of application and the application structure and needs aren't going to converge, you're going to have a fundamental issue with how you design systems across these basic ingredients, because the cost function is going to have different weights in front of them depending on which workload you are trying to serve. And that frequently has been used as a case for saying we don't want to go there. The question is no longer whether we want to go there or not. It's how we're going to go there. Because if we don't go there, we will see a situation that is actually not very friendly to either HPC or big data. So what is, in the end of the day, the benefits of a single system architecture? We've kind of talked through a few of these. The first big benefit is overcomes cost and complexity of moving data. So number one and number three, the workflow flexibility are highly related. What it means is the use of big data is not this shining new thing, I am now doing big data. You are doing, every piece of data now has intelligence associated with it, and any transaction, whether you're retrieving it, whether you're moving it, or you're modifying it, actually has this notion of being computed on, right? So workflows are changing. A great example of this, by the way, has nothing to do with data analytics, and something we're very familiar with in the traditional HPC world. It's called visualization. What did we do in the past, or still do predominantly today? We generate our models and our data. Then we take it over to a place where the visualization infrastructure and hardware is there. Sometimes we share it over a common file system, but sometimes we move it, and then we visualize, and then we bring it back. What it does is it increases tremendous latency, or introduces tremendous latency in what's called the cycle of the workflow, which is an iteration across generation, visualization, decision-making, and the next round of computation. Things like computational steering are very, very hard to do if the workflow itself is interrupted by these various, very specific phases that require data to be moved. Number two is actually very important to that very first top layer of the ecosystem I talked about. We've learned this, we as an industry have learned this the hard way. If you make it hard for developers to develop, to have a streamlined, sustainable, scalable investment stream into their application development, you will fail. Architectures that have actually never succeeded commercially, if you go look at them closely, and I won't take names here because that's not a good thing to do before a party, but you will see frequently, in fact, I would say in almost all cases I can recall, it wasn't a technical issue. It was simply a not enough interest issue. Not enough interest from an ecosystem to make that architecture successful by giving it applications that would then make the value of that architecture come up. And the last one then is improved total cost of ownership. Again, whether we are looking at a CIO who's saying, I'm going to buy a big data infrastructure for my CRM application, and a line of business GM that says, I'm going to buy a big honking HPC cluster to run my exploration or mission need. There's a total cost of ownership at every level, whether it's the storage subsystem, whether it's the compute, and especially with cloud-like delivery models for compute, there's tremendous TCO benefits of having a converged infrastructure, right? The thing that we have to then do, the imperative to realizing these benefits, the trivial case is, okay, we're going to do it. We're going to pick one of those 600 applications, and we're going to design the system for that. And if you're not that one, and you're one of the 599, life sucks. What do you do, right? Well, that obviously is not the right approach. So the real question is, how do you do a coordinated design effort around the key elements that make up a system? Compute, interconnect, memory, stitched together by both a usable, effective, and scalable software infrastructure. This is fundamental because of multiple things that are driving the interrelatedness of these components. A fundamental portion of that, a fundamental aspect of that is integration, right? If you look at integration, we've talked about this at least over the last 3 or 4 ISCs, compute and memory are getting integrated on package memory. We've talked extensively about the soon-to-be reality of interconnects getting more highly integrated with the processing elements in order to provide not just cost and energy benefits, but also provide greater functionality, implement some of these newer programming models more effectively, such as being able to deal with atomics. And then there's innovations around new technologies that fundamentally changed the way a system looks at, I am now doing a memory transaction versus a storage transaction. And being able to blur those lines has tremendous benefits to not only where you keep your data, but how many times you touch your data and what data you need to touch. Right? So this is the approach that is fundamental. If you don't do it, you will design for one and leave the other 599 out. If you design to this, what you do is you don't create a system definition. You don't create a system design. You create a system design surface from which you can generate multiple points of configuration. You know, how much compute boundness do you want to serve? What is the balance between the interconnect versus the compute? And now with some innovations I'll talk about in a second, how do you deal with the memory and storage hierarchy convergence as well? Right? So it gives you a surface. You don't have to go tell the non-600th, the other 599, sorry, you're not in the club. You can say, I have a system architecture, tell me how you want me to configure it, so you feel like you're the only one running on the system, right? That is the challenge, that is the task, and that is what we at Intel, along with our partners, are trying to innovate for this next generation, where I believe the answer is HPC and big data, not HPC or big data. Not simply because it is possible, but because that has to be the answer for the industry to move forward economically. So I drew this picture of, from here, where do we go? What we obviously don't want to do is force one side to be the other. You can't take, for instance, and say, okay, I'm sorry, Mr. Java, you can't do that anymore, or Python. You really need to learn MPI, right? Again, in order for these to succeed, the people who write codes for this or develop applications for this have to see it transparently to the extent they can, at least from a functional transparency. But everything underneath it can, from the resource manager file system and down to even the hardware, can actually be built so that you can configure it and use it for the purpose of either more on the data-intensive side versus the traditional HPC side. And that's why that is that infrastructure and the ability to configure that infrastructure that is the exciting next research frontier pursuit or the development pursuit for us going forward. Let me give you one example. You can say, okay, that's a nice high-level foil, and you can put ands between things and make it look like it's all possible. But let me give you one example, a very specific example of where this is possible. So if you look at the left-hand side, that's today. You have computes, right? The processor has caches, a cache hierarchy, in fact. And the hierarchy's increased over time as we've had more latency to hide, and we've had more Moore's law transistors to actually be able to provide caches. And then beyond that, what's in the processor itself, you have local memory, which is typically DRAM, right? And then suddenly it's no longer memory, it's storage, right? Because of the characteristics of how you look at the data in there in terms of the duty cycle of use, for instance, right? And then, of course, there's a file system that's, and then I could have drawn a few more levels here to tape and everything else, ending with the National Library of Archives or something. So what we've done effectively for the last few years is pushed the technology we've had to give us a few more levels in the hierarchy, right? The exciting thing about where we stand today is you get to actually not only do that through integration, but you actually get to also create new levels in the hierarchy. So if you look at the colors that are actually specifically chosen, amongst the, by the way, I'm a little colorblind, I should say, so I don't know what this color is. Is this orange or yellow? Orange, okay. Orange, that made for very fun undergraduate classes in circuit design because the resistors were color-coded, and I could never quite figure out whether I was getting 270 ohms or 2.7 k ohms, but that doesn't explain my grade in that class. I'm not going to be But these three is okay. So what we've not only got more cache levels, but we've actually taken local memory, which used to be DRAM, and moved it into in-package. You know, stacked memory is one of those new technology adoptions that's no longer new anymore, quite frequently done. Again, in the green, we've had the storage portion, where we've created hierarchies and basically moved the data closer to compute, or pre-staged it closer to compute, either on technologies like, you know, for instance, SSDs, and building around SSDs this notion of a cache hierarchy, if you will, called burst buffer, as an example. The one in blue is interesting. It's a fundamentally different approach and a new approach to being able to have something that also lets you not only have the latency and performance characteristics that may make you want to use it as memory, but potentially as storage as well, because you have non-volatility, right? An interesting question to ask then is, do you still have to retain all these levels of the hierarchy, right? If you had this capability, how would you configure it so that if you had a workload that looked like, I compute all the time and once in a while I go out and shovel large amounts of data, you can still do that, except the cost is lower, cost of transferring, because you're holding it closer to the processor. So this is an example, for instance, of in order to have that design surface, what you need to do is move from where we are today to being able to not only introduce incrementally new levels in the hierarchy, but introduce new capabilities in the hierarchy that allows you to treat memory and storage differently than you did before. We are trying to put this in context of a framework. Right? This whole notion of a design surface in a framework is then what makes it useful. I can talk about individual point innovations. You know, we've talked at length in this conference and others about the individual elements of what's in a Xeon Phi, or what's in OmniPath, or what's in the Lustre file system. The question is, how does it get put together to solve the following goals? One is it's scalable. It goes from small clusters to the biggest supercomputers of the world, because that design surface is one of the dimensions of that design surface is also scale, not just workload diversity. The second is it is compute and data centric. I mean, it is really an and it's not an or. It doesn't force the choice of an or. The third is, in order to do that, and even as we innovate and bring in new technologies, that we actually have standards-based programmability. Again, this goes to the fact that if you make it hard for technology to be used effectively, that technology either will never get used or it will get used very, very slowly. And the last one, which I haven't talked about much today, is to build this in such a way that the delivery model, whether it's in a traditional cluster or supercomputer versus a highly orchestrated environment like a cloud-based delivery model, is seamless. And it's not a trivial task to do it that way, because in a cloud-based delivery model, this framework, this design surface, and this dynamic configuration of the system for the workload it's running has to then be consistent with the cloud-based orchestration of that infrastructure. We already have things in play that today are working towards an early incarnation, if you will, of this framework. The framework is not, in some ways we can call it the Intel Scalable Framework, but it's really the ecosystem framework. What people do is they look at this as the ability to get to a persistent, scalable, interoperable platform, right? And that's really been the success of the x86 platform for the last few decades. The interesting and the exciting part is something we talked about earlier in this year with Argonne and Cray. And we are hoping to see this just be one small step forward into a broader ecosystem acceptance of this principle. And we are very happy to be working with multiple partners in taking this concept, which we will first potentially see in a big way in the Aurora system, but hopefully massively proliferated through multiple partners, through an ecosystems, what I would call treasure trove, to the industry in quick succession, right? So for us, I did want to talk about the fact that the scalable framework is how we bring this end together, how we take all of these innovations, make them useful, usable, and sustainable, how we do this in a way that allows greater participation by the ecosystem in all various aspects of the framework. And number three, how excited we are that we are on the doorstep of seeing this being the fundamental driver for the next set of growth that comes to whether you're a high-performance computing person or you're a big data person in this business, right? So with that, I'll end, and I'll see if you have any questions. I'm sure you'll have lots of questions on this, but we'll see how many we can do, Michael.
Okay, thank you. Raj, thanks for the refreshing talk. After 10 hours in meetings with vendors discussing details of products, this was really refreshing. Thank you very much. We have time for a few questions. We didn't want to leave you without giving you the chance to ask a question. And there is a microphone in the aisle here. There are 2 microphones, so if you have a question, please go to the microphone.
I'm also aware that some of you have voices that can put a microphone to shame, so feel free to use that as well.
Let me start with one first question, Raj. You talked about this single system architecture in a sense. Good for HPC, good for big data, good for both. And I'm wondering when Intel will come back into the system arena and create their own system.
So the answer
you talked about the system, but
yeah. So the answer is hopefully never. If you do this right,
yeah.
We've allowed both ourselves and our ecosystem partners, our OEM customers, to actually participate in a way that's good for them and good for us. At the end of the day, we bring a set of very targeted and finely honed skills, and they're not around some aspects of running a systems business. That is somebody else's business, and they're damn good at it, right? What I would see as success for this is not Intel has to do systems, because then really the scalable system framework failed. I mean, it's more like an internal tool. I would see success of this as enabling a much more thriving ecosystem, which is more effective at bringing new innovations to marketplace, which is more efficient in doing so, and therefore is the targeted innovation platform for the industry.
Okay, thank you very much. Any further questions, or is everybody waiting to run for the buses to go to the parties? We have one courageous person who is not hungry. Go ahead.
Hello. I noticed that you have names for the applications, you have names for the file system, you have names for the hardware. What you don't have is the name for the smart scheduler. Mm-hmm. So can I propose Mesos?
Yeah, absolutely you can propose. So, at this level of the architecture, obviously some things get what I would call conglomerated, right? But there are, especially when I made the cloud comment, right, this is very relevant, right? Do you have the ability to do resource management be nested under a broad data center orchestrator, or do you do it the other way around, which is you actually have the schedulers sit and the multiple kinds of orchestrators actually orchestrate portions of the system? That's actually an architectural decision, if you will. And you have to make that decision supported by a bunch of research. And in order to do that, you have to look at all of the mechanisms that allow you to look at everything from containerization to how you expose those services, if you will. Mesos is definitely clearly one of those frameworks, if you will, for doing so.
Okay, we have another question in the back first and then in the front.
So you were talking about big data and HPC, but what about taking the step further and enterprise IT and web scale, having a universal platform for all of that?
Yeah, great question. First is I got to leave something for next year, right? So, but the real answer is I did talk about it, maybe just not effectively. If you look at many of these big data applications, the data analytics applications, they are coming from where traditional business intelligence is getting transformed into what we call predictive adaptive intelligence, right? I made a statement about how CIOs and lines of business general managers actually have to work together now, right? In enterprise, we are seeing massive potential for the use of data analytics and therefore a very strong interest in procuring high performance infrastructure, but not for traditional high performance use, for data analytics. And that's a good thing because it's actually getting large corporations and silos within these corporations to actually start to collaborate and talk to each other.
Okay, go ahead.
Yes, Mr. Yang.
Yes, Raj. Another common phrase is the whole is more than the sum of the parts. And I was wondering from your perspective, what is the size of the HPC market? What is the size of the big data market? And then what is the size of the big data and HPC market?
So when you first asked that question, I didn't know what whole you were talking about. It was like, from a finance perspective, you could take the question a whole different way. But I think, you know, the IDC, other folks have a sizing of the traditional market and kind of this explosive data analytics market. And in many ways, that's hard to do, simply because what is a data analytics application if it's running on a Xeon Phi with high, you know, with InfiniBand or a custom fabric, right, with luster? I mean, what is it, right? At that point, do you classify it as growth of the HPC market? I actually think it's what's best to do, as opposed to looking at the growth that way, and that's the way we do it, is we say, what's the total growth of traditional HPC workloads in simulation modeling and these data analytics, and how much of them are affinitized to the characteristics of what we call high performance computing, right? Which is, it's stressing multiple system parameters, it's aggregated processing, and there is value to the performance experience, which many times comes down to solution urgency. So in that front, it's explosive growth. I mean, in the whole data analytics part, the world, the last question in the enterprise space, is still in test and dev, and it's less test and dev in the technology, it's test and dev on business models. What do I do? The beauty of data analytics or big data is you don't have your answer predetermined. How do I do this? Most people are going, if I have all of this, what could it enable me to do, right? And so it's very hard then to say this is a confined domain or a finite domain, and you can size that domain. It's really left to the ingenuity of how you would use what you have for a new economic value proposition, right? Why are we interested in this convergence? You asked the question that actually takes the economic point home. So if the growth is going to be dependent on unfettered use of these capabilities for innovation in the service, in the application, in the new use, you have to make the infrastructure not be the barrier. Either the cost of developing it, the cost of deploying it, maintaining it, right? And that's what we are trying to do, is make it efficient by not having to have a decision being made about you're investing in HPC or you're investing in big data.
Great, thank you.
Okay, ladies and gentlemen, let's thank Raj again for a fantastic presentation.
Thank you very much.